Welcome to iTTV for Form 5 Chemistry. The title of this lesson, Factors that Affect the Rate of Reaction, the Effect of a Catalyst. We've already had a look at the factors that affect a rate of reaction: temperature, concentration, particle size, and pressure. Those factors affect the rate of reaction by creating more collisions or causing more collisions to occur. When you have more collisions, the frequency of effective collisions will increase. Today's factor is the catalyst. What the catalyst does is, it basically changes the activation energy needed. It can either lower the activation energy or increase the activation energy. And when the activation energy changes, the frequency of effective collisions will also change. Let's have a look at the catalyst. Effect of catalyst. A catalyst is a chemical substance that changes the rate of reaction, but it remains chemically unchanged at the end of the reaction. So a catalyst doesn't take part in the reaction. It is not a reactant and it is not a product. Mainly, the catalyst is basically something that we would write in a reaction equation above the arrow. Also, it is unchanged chemically, which means that most catalysts can be reused. Let's go up to the board and write an equation out for the decomposition of hydrogen peroxide, so that you understand how to write the equation and where to list out your catalyst. So the decomposition of hydrogen peroxide. Hydrogen peroxide is H2O2. When it decomposes, it produces water and oxygen. Let's quickly balance the equation. Over here we've got 2 oxygens, here we have 3. So we go from compound to compound first. We'll try to fix this by putting a 2 here. Now the problem is we've got 4 oxygens here, but only 2 on this side. So we balance that by putting a 2 in the front here. Now what about the catalyst? Well, in this reaction, the catalyst we use is manganese 4 oxide. MnO2. So what we do is we list the catalyst, like I said, above the product sign. So you write here MnO2. So remember, the catalyst is not written in the equation itself, but above the arrow. And remember, it is chemically unchanged, so you can reuse your catalyst most of the time. Let's go back to the slide. Effect of a catalyst. A positive catalyst increases the rate of a reaction. A negative catalyst decreases the rate of reaction. So remember, a catalyst can either speed up the reaction or slow it down. Most of the time, we are going to be dealing with positive catalysts. The mass of the catalyst remains unchanged throughout the reaction. Most catalysts are either transition elements or compounds of transition elements. And we learned this when we did the periodic table and looked at transition elements. One of the specific or special characteristics of transition elements is that they are widely used as catalysts. The example that we listed on the board, which is the decomposition of hydrogen peroxide, uses manganese oxide. Now, manganese is a transition element. So here you have an example of a compound of a transition element being used as a catalyst. Characteristics of a catalyst. Different reactions require different catalysts. Most catalysts only will catalyze or affect one specific reaction. very similar to enzymes that we have in our body. A catalyst does not change the quantity of the products. Now this is very important. Remember, a catalyst cannot give you more product. What a catalyst does is, it gives you your product faster. Now let's go up to the board and sketch a graph to show a reaction that uses a catalyst and compare it to a reaction that does not use a catalyst. So let's start by just drawing in our axis. And let's take the decomposition of hydrogen peroxide as our example. What we're doing is, we're going to record the volume of oxygen gas that is being produced. Because it's a product, our graph should look something like this. But this is with no catalyst. Let's label this, yes? So here we have no catalyst. If I was to use a catalyst, what I would find is that I would get a faster rate of reaction, but the key here is to remember I don't get more product, which means that I should get a steeper gradient, but my final product is the same amount. So remember, with a catalyst, your rate of reaction, especially a positive catalyst, will be faster, but the amount of product is the same. So let's just label this. This is with a catalyst. So with a catalyst, your rate is faster because your gradient is steeper, but the amount of product, the volume of oxygen gas being produced in this case, is going to be the same amount. It's just that you get it faster. Let's go back to the slide. A catalyst remains chemically unchanged after the reaction. The physical state of the catalyst might change after the reaction. Now, when we mean the physical state, it means that you might have lumps of catalyst, and at the end you might have a powdered catalyst left behind. So the physical state can change, but the mass and the chemistry of it are unchanged. Only a small amount of catalyst is required to catalyze a reaction. And this is a benefit. Because you only need a little amount, the cost of using a catalyst is reduced. If a bigger quantity of catalyst is used, then the rate of reaction will increase. So if you use more catalyst, your rate of reaction will be even faster still. Experiment 1. To investigate the effect of catalyst on the rate of reaction. The decomposition of hydrogen peroxide. 2 hydrogen peroxide produce 2 water and oxygen. The catalyst is manganese 4 oxide, MnO2. So in the first reaction, where hydrogen peroxide is decomposing by itself, it takes a very long time. In the second reaction, where we have hydrogen peroxide and the catalyst manganese 4 oxide, the reaction is much faster. In the first reaction, we observe no effervescence, which means we can't even see the oxygen gas being produced. In the second reaction with the catalyst, our observation is that the effervescence is visible and the glowing wooden splinter is burning with a bigger flame. Experiment 2. To investigate the effect of the amount of catalyst on the rate of decomposition of hydrogen peroxide. Once again, our equation is 2 hydrogen peroxide produce 2 water and oxygen. Our catalyst is still the same, manganese 4 oxide. Our apparatus is set up as shown. The conical flask is attached through a delivering tube to a burette. The volume of oxygen produced will be recorded at the correct intervals of time. What we get is a graph that you see on the slide. Graph A is when we use 0.2 grams of manganese oxide. Graph B shows 0.4 gram of manganese oxide. If you analyze the graphs, what you see is in reaction B, when you use more of the catalyst, the gradient is steeper, which means that the rate of reaction is higher. So try to understand this, students, that if you use more of the catalyst, your reaction is going to be faster. Remember, the amount of product is unchanged. So if you use more catalyst, you will get a higher rate of reaction. The gradient of the graph for experiment B is steeper than that of experiment A. The rate of reaction of experiment B is higher. Conclusion: the greater the amount of catalyst, the higher the rate of reaction, but the amount of product would be the same. Kinetic theory. The particles in matter are in continuous motion and they collide with each other frequently. Collision theory. Collisions between particles will result in a chemical reaction. These collisions are known as effective collisions. The rate of reaction is determined by the frequency of effective collisions. Conditions for an effective collision. The particles must collide with energy equal to or more than the activation energy. And B, the particles must collide in the correct orientation. So what kinetic theory says to us is that we understand that particles are in constant motion. These particles that are constantly moving are constantly colliding with each other. Now, it's when this colliding occurs that a reaction is going to take place. But we need to understand that not all collision give us a reaction. If your particles collide in the correct way with the correct energy, then we get a reaction. These type of collisions that give us a reaction, we call them effective collisions. And the effective collision is determined by two things. One, the amount of energy the particles that are colliding have, which is known as your activation energy. And secondly, they must collide in the correct way, which means they must have what we call the correct orientation. Let's go up to the board and try to understand these two concepts for creating or getting an effective collision. But before we do that, we'll just clean the board up first. So let's have a look at the first factor, which is orientation. If you have a particle A that is traveling this way and it collides with another particle B that is traveling in this direction, notice that they're hitting off center. Because they're hitting off center, when they collide with each other, all they do is they bounce off each other. They will bounce away like this, bounce away. This is not going to give us a reaction. So this is what we say to be not the correct orientation. But if your particles collide head on, that means A is traveling in this direction and B is traveling in this direction, like so. When these two collide, they are going to produce a reaction. Assuming that they have the enough amount of energy, which is the activation energy, this will produce a reaction. So this is what we mean by correct orientation. This on top is not the correct orientation. this is the correct orientation. So the first thing you need for an effective collision is you must have the correct orientation. The second thing you need for a correct reaction or an effective collision is you got to have the correct amount of energy. So let's go to the second part here and draw an energy profile. This is energy. Now, whenever you do a reaction, you have the energy of your products and your reactants. So here are my reactants. Here are my products. It doesn't necessarily have to be that the reactant has more energy than the product. It could be the reactants are here and the products are up here, meaning they have more energy. But for today, we'll just leave it as this. Now, what you get is a graph that spikes up like this and then comes down here, like so. The energy difference from here all the way to the top here is known as the activation energy. Now, in order for you to get an effective collision, basically you need two things. One, you must have the correct orientation, and two, you must have enough activation energy, which is the minimum amount of energy that the particles, in this case particles A and B, must have so that they create an effective collision. So remember, the two things you need for an effective collision: correct orientation, and number two, you need to have enough activation energy. If you have both of these, then you will have what we call an effective collision. Let's go back to the slide. Example. We'll have a look at the decomposition of hydrogen peroxide. Remember, an ineffective collision due to incorrect orientation. Remember, you get an effective collision if you have sufficient energy and correct orientation. Activation energy. The minimum energy the colliding reactant particles must possess in order to result in an effective collision. The energy profile diagram. Now, the reactants and the products are connected by a curve. This value from the reactants to the top of the curve is known as the activation energy. The little symbol for activation energy is a capital E with a small a. The effect of catalyst. A catalyst will lower the activation energy needed by providing an alternative reaction pathway. So, what does a catalyst do? Well, the catalyst lowers your activation energy if it is a positive catalyst. So let's just look at these positive catalysts for a moment. Now, if you have a positive catalyst, it will lower your activation energy by providing an alternative reaction pathway. And basically, your activation energy graph changes. Let's go up to the board and sketch in what occurs if a catalyst is used. So, over here, we have our graph of activation energy. The activation energy is up here. But if you use a catalyst, what happens is this value becomes less. So what you get is a curve that goes up and then comes down here, which means that the activation energy with a catalyst is only this value here. So this is the activation energy with a catalyst. And because your activation energy is lower, it means more collisions will produce effective collisions, because more of the reacting particles have enough energy to create that effective collision that we are looking for. So remember, what does a catalyst do? It lowers the activation energy by providing an alternative reaction pathway. Let's go back to the slide and continue with our lesson. So, there will be more effective collisions, therefore the rate of reaction will be higher. So remember what a catalyst does. The catalyst lowers the activation energy by providing an alternative reaction pathway. Your frequency of effective collisions will increase. Therefore, your rate of reaction will be higher. Now, finally, what's important is that you understand or recall some of the reactions that contain or use catalysts. The first one, the most important one, was the one we looked at earlier, which was the decomposition of hydrogen peroxide. Another very important reaction that you need to recall that uses a catalyst is when we use a metal that is reactive, like for instance zinc, and react it with hydrochloric acid. Here you can increase your rate of reaction by using copper sulfate as your catalyst. So if you ever see a reaction that is zinc plus hydrochloric acid and they say copper sulfate is added, please understand this is also an example of a reaction that is using a catalyst. Let's write this equation down on the board so that if you ever see it, you will recognize it. So remember, the first one was the decomposition of hydrogen peroxide. So the first reaction you want to look at is the decomposition of hydrogen peroxide. Hydrogen peroxide in the presence of the catalyst manganese 4 oxide, MnO2, O2, let me just redo this 2, will decompose to become water plus oxygen. To balance the equation, we put a 2 in front of the hydrogen peroxide and a 2 in front of the water. So hydrogen peroxide in the presence of the catalyst manganese 4 oxide will decompose to produce water and oxygen. Another catalyzed reaction that commonly comes out in the exams is the reaction between zinc and hydrochloric acid. Here, your catalyst is copper sulfate. Copper sulfate, CuSO4. Your product will be zinc chloride plus hydrogen gas. So remember the two reactions you need to keep your eyes open for. The decomposition of hydrogen peroxide using manganese 4 oxide as the catalyst, and when zinc reacts with hydrochloric acid, where we use copper sulfate as the catalyst. So remember the key things about your catalysts. Your catalysts are usually transition elements or compounds of transition elements. A catalyst is usually specific. A catalyst does not change chemically but can change physically. Only a small amount of catalyst is needed. Remember, if you use more catalyst, the rate of reaction will be even higher. Remember what a catalyst does. It provides an alternative reaction pathway and lowers activation energy, so your frequency of effective collisions increases. And finally, students, please remember the key reactions that we do in the lab that use catalysts. The decomposition of hydrogen peroxide or the addition of a metal like zinc to hydrochloric acid, where we use copper sulfate as our catalyst. That's all the time we have for this lesson. Thank you for watching ITTV.